Once again, we are in theta degrees here. We have our pole that's right here in the middle. Our measurements, we have 0 degrees, 30 degrees, 60 degrees, 90 degrees, 120, 150, 180, 210, 240, 270, 300, and 330. Okay, this is our measure. It's our angle of rotation, our theta value. It's our angle of rotation. We have R, which is your distance from the pole. And how we measure our distance from the pole is by using the circle. Because by definition of a circle is a set of points that are equal distant from a given point. Or a given point is going to be the pole. These circles will measure a distance from that pole because all these points are equal distance from this point right here. So I can label this as ever as I want, depends on my units. I'm going to go every 2 to give me 1 unit. So this is 1.5. This would be a value of 2. This would be 2.5. This would be a value of 3. If I wanted to, I could label every circle. So I could go out to 6 units here. If I want to go every circle as 2, I could go out to 10 units. So it depends on what your units are within your problem. With this, we have a ordered pair. This ordered pair is going to be r theta. So if I'm going to label the point 2 and 30, my R value is a value of 2. My angle of rotation is 30 degrees. So I go out to my 2 units out and I rotate up 30 degrees. You can use this, go either direction with this, just like labeling a point X, Y. You could go left and right X and then go up and down Y. Or you could go up and down Y first and then left and right X. It does not matter. You could go the idea of I'm going to rotate 30 degrees out and then I'm going to count 2 units up. That would be fine. Or I could go 2 units out and rotate up 30 degrees and just follow that circle around. It's up to you, whatever works. So this would be the ordered pair 2 and 30. Go ahead and label the other ordered pairs 3, 1, 10. 1, 2, 10, and -3, 300. Go ahead and label those points. That would give us our 3, 1, 20. Then we have 1, 2, 10. Would be this point. And then, and just like we did in trig class, this here tends to be the mystery one. If I go -3, 300. If I go out the 300 line here and put this point, this would be the point 3 and 300. But I need to go a -3 along the 300 line. So if I go -3 along the 300 line, I start here, counting out here would give me a +3. To go -3, what do we have to do? Brendan, what do we have to do? Go the opposite direction. So what line would we go out then? What would be opposite to 300? 120. So I would go to this exact same point, and I can label that -3 and 300. Okay, so when I deal with negatives, I just go to my degree angle, and I just go the opposite direction. If we graph the ordered pair, or graph this function here, 1 plus 2 cosine of theta, I guess we can use the graph that we have up top there. Okay, when graphing functions, there's no really easy way of graphing polar functions. And once again, as we talked about in trig class, a lot of computer graphics was done by use of polar functions. When you go into the curvature world, it's a lot easier, and the functions become a lot more less difficult to work with when dealing with it in the polar direction rather than in a Cartesian XY polar or XY system. So as you go through this, we have values of theta and we have the value of r. And the only thing we could do is plug in values of theta, and most of the time you can get away with multiples of 30. And all that you make sure you're in a degree mode in your calculator. All that you can do is type in values of theta and solve for r. So I have 1 plus 2 cosine of 0, 1 plus 2 cosine of 30, 1 plus 2 cosine of 60. Go ahead and plot the point setting up above. Now, your calculator, once again, will be a little bit nicer for you if you want to work it through your calculator. You need to make sure you're in a degree mode. Okay, make sure you're in a degree mode. Then if you type in to your Y1, was it 1 plus 2 cosine theta? 1 plus 2 cosine of x. Now, it doesn't give you theta, which is fine. Okay, it gives me just my x, but all I'm worried about is I'm worried about getting y values here. So I could do one of two things. If I go to my table setup, I'm going to start at 0 and increase by 30s. Okay, so if I go to second and window, that's my table setup. I can start my table at 0 and I want to increase my values by 30 each time. Now if I go to my table, which is second and graph, what I get is I get all my values. Over here, 3, 2.72, 1, 0. We get the values that you just came up with. It's a little bit easier to work through. You could also work through the second and calculate values. Okay, it's just going to give you a straight line. You don't really worry about that because all that you worry about here is if I have 0, what's my y value? If I have 30, what's my y value? Well, it's going to give me some problems because I'm outside my range. So it's a little bit easier if you would go to table and get all your values that way. If you want to sit there and click it back through the calculator and just type in the values, that is fine too. Just showing you what your calculator, KYC here, know your calculator. So we have 3, 2.721. What's 120? Brown, what do you got? 0. Then negative. What's 150? Negative 1, negative 0.7, 0, 1, 2, 2.7, and 3 is our values. So as we go along and graph this, at 0, at 3, at 30 we are at 2, at 60 we were at 1, at At 90, we are at 0. At 120, we're negative 0.7. Let's see. I botched that up, didn't I? At 90, we're at 1. At 20, we were at 0. Is that right? Then 150, we're negative 0.7. 180, negative 1. Then negative 0.7. Need to make sure we go back. Then we had 0. At 270, we're at 1. Then we are at 300, we're at 2. Then 2.7 is our points. Now, when you're graphing these are all going to be curved. And we just go in numerical order from 0 to 360 as we go along. So we go from 0 to 30 to 60 to 90. We don't use a straight edge here. To 120 to 150 to 180 to 10, then back to 0. And what this graph is called, this is called a lemon. Too bad we didn't do St. Patrick's Day on this one. Okay, a lemon with a loop. So you have a little loopy in there. We also can have lemons without a loop. We have cardioids, we have 3-leaf rows, we have 4-leaf rows. Once again, these are a lot easier to graph in a polar coordinate system than it is a Cartesian coordinate system. We can take a look at conversions from polar to Cartesian and Cartesian to polars. If we would take any point, here, we can label this point r and theta. This would be the ordered pair r and theta. We can also look at this as an xy coordinate system. In an xy coordinate system, we can move out x and we can move up y. In the polar coordinate system, this is our angle of rotation theta. This is our distance r. And no matter what coordinate system we are in, r and theta or x and y, we get to the exact same point. Well, what we have now created with the x, y, and the r, and the value of theta is a nice little handy-dandy right triangle. And in that right triangle, we have our trigonometric guardian. SOHCAHTOA. Our trigonometric guardian would say the cosine of that angle theta is equal to what over what, Jade? X over r. Which tells us if we multiply both sides by r, x is equal to r cosine of theta. We can look at that triangle again and look at the sine of theta. Nolan, what's the sine of theta? What's our trigonometric guardian say about the sine of theta? What would the sine of theta equal up here?
Y over r.
Y over r. So we would have y over r. Once again, we can multiply both sides by r. So y would equal to r times the sine of theta. Our trigonometric guardian would also say tangent of theta is equal to y over x. So this allows us to basically take x and y, which is the Cartesian coordinate system, x and y, and move that into r's and thetas, which is the polar coordinate system. So it allows us to be able to transfer from Cartesian to polar, polar to Cartesian. We have also our good old buddy Pythagoras. Our good old buddy Pythagoras. What would our good old buddy Pythagoras say in that triangle, Isaac? I don't see any A's, B's, and C's.
X squared plus y squared equals r squared.
X squared plus y squared is equal to r squared. Or r would equal the square root of x squared plus y squared. We want to convert our polar coordinates into a Cartesian coordinate system. We have r equals sine of theta. We want to convert into Cartesian, which means we want to get rid of all the r's and thetas and change them to x's and y's. Well, the r is an ugly x and y, so let's wait to see what happens with the other side here. I have r is equal to 6 times the sine of theta. Sine of theta is y over r. Multiplying both sides by r, we have r squared is equal to 6y. Now we got an r squared, which is a little bit easier to work with. R squared is equal to x squared plus y squared. So I have x squared plus y squared is equal to 6y, which in a conic section world, it's more acceptable if you have it equal to a constant and you collect your variables. So we have x squared plus y squared minus 6y is equal to a value of 0. Go ahead and do the second one here. Make the same type of substitutions. Jacob, what do you come up with?
X squared plus y squared minus 4x equals 0.
That is correct. X squared plus y squared minus 4x equals 0. Now, what I suggest you do, I don't sit here and memorize these things here. I think it's a little bit easier. I always refer back to this triangle. Because from this triangle, hopefully I can say the sine of theta is equal to y over r, cosine of theta is equal to x over r, x squared plus y squared equals r squared, tangent of theta is equal to x over y over x. I can go back to that triangle and be able to come up with my values that I need, rather than sitting there and trying to memorize these values here. Now, if you use them enough, you'll remember cosine, or x is equal to r cosine theta, y is equal to r sine of theta. But I always refer back to that triangle mentally to be able to come up with these relationships. So I have to convert into a polar coordinate. I have the ordered pair negative 5, 12. So x is negative 5, y is 12. Okay, I want to change this into r's and thetas. Okay, I want to change this into r's and thetas. So if I look at my ordered pair here, x is negative 5, y is 12. What we need to convert this into is to r's and thetas. So I need to know what is my distance r and what is this angle of rotation theta. Once again, converting this just straight into a triangle. We have negative 5 here, and we have 12 here. Or you can think about r squared is equal to x squared plus y squared. It runs you right into Pythagorean theorem. If you know your Pythagorean triples, r is a value of what here? Ella?
13.
R is a value of 13. Now what you need to come up with is this angle of rotation theta. Well, what I suggest you do is throw an alpha in there. And the tangent of alpha is equal to 12 over 5. I would not worry about the negative sign there. And take the inverse tangent of 12/5. That will get you alpha, and then you can use your noggin to be able to come up with theta. Janae, first off, what do you get alpha to be?
67.4.
Okay, so this angle here is 67.4 degrees. Now I need to convert this into theta, which is this angle right here. Well, if this is 67.4, what would we have to do to find this angle of rotation then, Janae? Subtract from 180. So we have 180 minus 67.4. So my theta value, 112.6. So my r theta would be 13, 112.6 degrees. Convert to Cartesian. Okay, I'm in a polar and I'm in Cartesian. So I have r and theta. I need to change this to x and y. Well, x is equal to r cosine of theta. Y is equal to r sine of theta. Might be better if I change this into a 210. So we have, let's see, 8 cosine of 210 and 8 sine of 210. We have a reference angle of 30 there. So we have 1, 2 square root of 3. Negatives with both of those. So we have, let's see, 8 times the cosine, which is negative square root of 3 over 2. So we have negative 4 square root of 3. And 8 sine is 8 times negative 1/2. So we have negative 4. So we'd have the ordered pair, negative 4 square root of 3 and negative 4. Once again, this is polar coordinates. What we did in about a week. Since we're a second time through, it's going to be a little bit quicker. It's like everything we've done here in class. But it's also one of those things where you should see some familiarity with this. See some familiarity with this, so it should not be that too, or nothing too difficult for you. Once again, tomorrow we have our last topic to cover, which is complex imaginary numbers with polar coordinates. We will cover that tomorrow. Friday will be sort of a worksheet that will combine everything together. Monday will be a review day. Tuesday will be a quiz. Wednesday will be a review day, and Thursday, Friday will be your unit tests over this chapter. Then when spring break. It will go by fast for you. All right, solutions, I posted them. Hopefully I did. The rest of the time is yours.